What if the Big Bang wasn't really the beginning of everything? Welcome to Sleepy Origins. Tonight, we're diving into one of the biggest mysteries in science. What may have existed before the universe? Whether time itself is real? And why modern physics keeps breaking apart near the origin of reality? The deeper scientists look into space, the stranger existence starts to feel. Before we begin, what's your personal theory about what came before the Big Bang? And where are you watching from tonight? Drop your city and thoughts in the comments. Get comfortable, and let's journey back to the edge of the universe itself. 14 billion years ago, there were no stars, no galaxies, no planets drifting through cold black space. In fact, according to the best models modern physics can currently offer, there may not even have been space itself yet. No direction, no distance, no ticking clock, quietly moving events from one moment into the next. And that is where the story immediately becomes uncomfortable. Because the human mind depends on time so completely that trying to imagine reality without it almost feels like trying to imagine a color the brain was never designed to see. When most people hear the words Big Bang, they picture an explosion somewhere in the darkness of space, a giant blast throwing matter outward into an already existing universe. But that image is misleading in a very important way. The Big Bang was not an explosion inside space, it was the rapid expansion of space itself. Every galaxy, every atom, every future star system was compressed into an unimaginably hot and dense state before space began stretching outward in all directions at once. There was no center to the explosion, because there was no outside environment surrounding it. The universe was not expanding into empty darkness. The expansion created the very distances that would later separate galaxies by billions of light years. That distinction changes everything about the question people have asked for generations. What happened before the Big Bang? Because if space itself began during that event, and if time is woven into space, as Einstein's relativity suggests, then before may not work the way human language assumes it does. The deeper scientists looked into the mathematics of the early universe, the stranger the situation became. Time may not have been sitting there waiting for the universe to appear. Time itself may have emerged together with the universe in the first fraction of a second after the Big Bang began. That idea sounds abstract until you slow down and think about what time actually does. Every memory you have depends on it. Every movement, every heartbeat, every sunrise, every death. Human beings experience existence as a sequence. One event causes another. The past becomes the present. The present slips into the future. But physics increasingly suggests that time is not some invisible cosmic river flowing independently through reality. Instead, it may be part of reality itself, flexible, stretchable, and possibly absent under extreme conditions. Einstein was one of the first people to truly break humanity's intuitive understanding of time. His theory of relativity showed that time is not universal. Clocks move differently depending on gravity and speed. Near massive objects, time slows down. Astronauts traveling at enormous velocities technically age slightly slower than people on Earth. These effects are small in daily life, but they become dramatic near black holes or across cosmic distances. the universe does not contain one single master clock. Reality bends time depending on circumstances. And if time can bend, stretch, and slow down, physicists began wondering whether it could also have a beginning. The equations describing the expanding universe eventually led scientists backward toward a moment when density and temperature become almost impossible to comprehend. Galaxies move apart today, which means they were closer together in the past. Run the cosmic film backward far enough, and everything collapses toward an extreme state of compression. Temperatures rise into trillions upon trillions of degrees. Matter as we know it cannot survive. Atoms break apart. Even subatomic particles dissolve into raw energy. The universe becomes a violent ocean of radiation, so intense that the laws governing ordinary reality stop behaving normally. And then comes the truly unsettling part. At around what physicists call the Planck epoch, less than a trillionth of a trillionth of a trillionth of a second after the Big Bang, modern physics breaks down completely. General relativity, which describes gravity and the structure of space-time, collides with quantum mechanics, which governs the microscopic world. Both theories are incredibly successful in their own domains. Both predict reality with astonishing accuracy. But at the beginning of the universe, they refuse to cooperate. The equations stop making physical sense. This is often described as a singularity, a point where density becomes infinite and known physics collapses. But many scientists suspect the singularity is not a real object. It may instead be evidence that human theories are incomplete, a warning sign that the map ends there, not necessarily reality itself. That distinction matters because it leaves open a possibility both fascinating and frustrating. The universe may not truly begin at the singularity. The singularity could simply represent the limit of our current understanding. For centuries, humans assumed the universe was eternal and unchanging. Ancient civilizations imagined endless heavens cycling forever above Earth. Then, modern astronomy shattered that picture piece by piece. In the 1920s, astronomer Edwin Hubble discovered something astonishing while observing distant galaxies. Almost every galaxy appeared to be moving away from us. More importantly, the farther away a galaxy was, the faster it seemed to recede. The universe was expanding. Suddenly, the cosmos no longer looked eternal and static. It looked dynamic, alive in a sense. A universe expanding today implied a smaller universe yesterday, and eventually, a beginning. At first, many scientists resisted the idea because it sounded strangely similar to religious creation stories. Even Einstein reportedly disliked the implications early on. But evidence kept accumulating. Decades later, another discovery transformed the Big Bang from controversial theory into the dominant cosmological model. In 1965, two radio astronomers named Arno Penzias and Robert Wilson accidentally detected a faint microwave signal coming from every direction in space. They thought something was wrong with their equipment. They cleaned the antenna. They investigated interference. Nothing removed the signal. Eventually, scientists realized they had discovered something extraordinary: leftover radiation from the early universe itself. Today, this glow is called the cosmic microwave background radiation. It is essentially ancient light released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could finally travel freely through space. Before that moment, the universe was opaque, a blinding plasma trapping radiation everywhere. The microwave background became one of the strongest pieces of evidence that the universe truly evolved from an incredibly hot and dense early state. And yet, even with this evidence, the actual origin remains hidden behind a wall physics still cannot penetrate. There is something strangely humbling about that. Humanity can build telescopes powerful enough to peer billions of light years across space. We can detect invisible gravitational waves caused by colliding black holes. We can calculate the age of stars and measure the chemistry of distant planets. But when we approach the first instant of existence itself, reality becomes foggy again. Some physicists suspect this fog exists because the universe at its beginning was fundamentally quantum in nature. At microscopic scales, reality behaves probabilistically rather than predictably. Particles fluctuate in and out of existence. Empty space is not truly empty. Instead, it seethes with temporary energy fluctuations known as quantum fluctuations. This leads to one of the strangest possibilities modern science has proposed. The universe may have emerged from a quantum event. Not from nothing in the ordinary sense, but from a quantum vacuum. A state that appears empty, yet still contains physical laws and fluctuating energy fields. In certain interpretations, tiny quantum fluctuations in the early cosmos could have triggered a rapid inflationary expansion, causing the universe to balloon faster than the speed of light for a brief instant. Inflation theory helps explain several mysteries about the universe, including why space appears so remarkably uniform across enormous distances. But it also introduces unsettling implications. If inflation can happen once, perhaps it can happen repeatedly. Some scientists believe our universe may be only one region inside a far larger cosmic system, constantly producing new universes, like bubbles forming in an endless ocean. And suddenly, the question changes again. Not what happened before the Big Bang, but whether our Big Bang was simply one event in a much larger reality humans can barely imagine. Still, there is another possibility that many physicists quietly consider just as important. The human brain may be trying to force reality into categories reality never obeyed in the first place. Humans instinctively assume every event requires a prior cause. Every effect follows something else. But causality itself depends on time. Without time, cause and effect lose their ordinary meaning. Asking what came before time may be like asking what lies south of the South Pole. The structure of the question may collapse before the answer even begins, and that may be the most unsettling idea of all. Not that the universe hides its origin from us intentionally, but that reality near the beginning becomes so alien that human intuition stops functioning entirely. Imagine standing at the edge of a frozen ocean during absolute darkness. Somewhere beneath the ice, enormous movements are happening. Pressures shifting, cracks spreading silently through the deep. But the surface reveals almost nothing. That is where cosmology exists today. Scientists can observe the after effects. They can reconstruct parts of the story, but the first instant itself remains buried beneath a layer of physics humanity still does not fully understand. Even now, researchers search for clues hidden in gravitational waves, quantum gravity theories, and subtle irregularities in ancient cosmic radiation. Some hope future discoveries may eventually reveal whether time truly had a beginning, whether another universe existed before ours, or whether the concept of before never applied at all. Because the closer science moves toward the birth of reality, the stranger reality appears to become. And somewhere beyond that wall of fire, beyond the first measurable fraction of a second, lies one of the oldest mysteries humans have ever asked beneath the stars. Was the Big Bang truly the beginning of everything, or only the moment the universe first became visible to us? There is a point in the history of the universe where human physics simply stops working. Not gradually, not politely. It breaks. The equations that can predict the movement of galaxies, the collapse of stars, the bending of light around black holes, and even the birth of atomic particles suddenly begin producing impossible answers. Density becomes infinite. Temperature becomes infinite. Gravity becomes infinite. And in science, infinity inside an equation is usually not a triumph. It is a warning sign, a signal that something deeper is missing. This is the place physicists call the singularity. And for decades, it has sat at the center of cosmology, like a dark wall no one has fully crossed. If you could somehow travel backward through time toward the beginning of the universe, everything around you would become stranger with every passing fraction of a second. Galaxies would move closer together. The universe would grow hotter and denser. Stars would vanish. Atoms would be crushed apart. Space itself would shrink. Distances that now take billions of years for light to cross would collapse toward almost nothing. Eventually, all the matter in the observable universe would compress into a state beyond ordinary comprehension. Not a giant fireball floating in darkness, but reality itself, folded into extreme conditions where the known laws of nature lose their stability. And this is where one of the most unsettling discoveries in modern science emerges. The deeper humans investigate the beginning of existence, the less reality resembles common sense. The singularity first appeared naturally inside Einstein's equations of general relativity. Einstein had radically changed humanity's understanding of gravity in the early 20th century. Instead of treating gravity as an invisible force pulling objects together, he described it as the curvature of space-time itself. Massive objects distort the geometry around them. Planets orbit stars because they follow curves through warped space-time. The theory worked astonishingly well. It explained the orbit of Mercury more accurately than Newton's gravity. It predicted black holes before they were widely accepted. It predicted gravitational lensing, time dilation, and gravitational waves long before technology could confirm them. Even today, general relativity remains one of the most successful scientific theories ever created. But hidden inside those beautiful equations was a disturbing implication. If gravity always attracts matter inward, then tracing cosmic expansion backward suggests the universe once collapsed into an infinitely dense state. The mathematics led not to a smooth beginning, but to a boundary where space and time themselves appeared to end. At first, many physicists suspected this conclusion meant the equations were being misused. Infinity made them uncomfortable. Nature rarely behaves infinitely in measurable ways. But as researchers continued studying black holes and cosmic expansion throughout the 20th century, the singularity problem refused to disappear. In the 1960s, physicists Roger Penrose and Stephen Hawking developed powerful mathematical theorems suggesting singularities were not merely odd accidents. Under certain conditions, general relativity seemed to require them. If enough matter collapsed inward, space-time itself could curve into a point where known physics breaks down completely. That realization changed cosmology forever, because suddenly, the Big Bang was no longer simply an idea about expansion. It became tied to one of the deepest unsolved problems in science. What happens when reality reaches conditions so extreme that the universe can no longer be described by current laws? The problem becomes even stranger when quantum mechanics enters the picture. Quantum theory governs the microscopic world: particles, radiation, probability, uncertainty. It describes reality at scales smaller than atoms with extraordinary precision. Modern electronics, lasers, computers, and much of modern civilization exist because quantum mechanics works. Yet, quantum physics views the universe very differently from relativity. Relativity describes smooth space-time geometry. Quantum mechanics describes fluctuating uncertainty and probabilities. Under ordinary conditions, physicists can use each theory separately without major issues. But near a singularity, the universe becomes both incredibly massive and unbelievably tiny at the same time. And that is where the conflict begins. Gravity becomes enormously strong on microscopic scales. Quantum fluctuations become violent. Space-time itself may start behaving unpredictably. Instead of smooth geometry, reality may become turbulent, almost foamy, with tiny distortions appearing and vanishing constantly. Some physicists describe this hypothetical region as quantum foam. Not foam in the literal sense, but a chaotic state where the structure of space itself becomes unstable. Distances and durations may lose their ordinary meaning. Cause and effect may no longer behave normally. It is difficult to overstate how alien this would be. Human beings evolved to understand falling rocks, flowing rivers, daylight, shadows, and physical objects. Our brains were never designed to intuitively grasp what happens when the entire universe shrinks smaller than a subatomic particle, while gravity and quantum mechanics violently collide. And yet, the mathematics suggests something extraordinary may occur there. Some researchers believe singularities are not physical objects at all, but signs that general relativity is incomplete. In other words, the equations may be breaking before reality does. Just as Newton's gravity eventually failed under extreme conditions and had to be replaced by Einstein's relativity, relativity itself may eventually require a deeper theory beneath it. This is one reason physicists search so intensely for a theory of quantum gravity, a framework capable of uniting relativity and quantum mechanics into one coherent description of reality. So far, nobody has fully succeeded. String theory became one of the most famous attempts. Instead of treating particles as tiny points, string theory proposes that the fundamental ingredients of reality are unimaginably small, vibrating strings. Different vibrations create different particles. In some versions of the theory, space may contain extra dimensions curled up beyond human perception. Under these models, singularities might disappear entirely. The universe may avoid collapsing into infinite density because quantum effects or higher dimensional structures prevent it from reaching that impossible state. Loop quantum gravity offers another possibility. In this approach, space itself may be quantized, built from incredibly tiny discrete units rather than being infinitely smooth. If true, there could be a fundamental limit to how compressed the universe can become. Space-time might resist infinite collapse the same way matter resists compression inside atomic structures. Some loop quantum gravity models even suggest the Big Bang was not the absolute beginning, but a bounce. A previous universe may have collapsed inward before rebounding outward into the expanding cosmos we inhabit now. That idea sounds almost mythological at first, universes dying and being reborn in endless cycles. But mathematically, some physicists argue it could avoid the singularity problem altogether. Still, no theory has yet been experimentally confirmed, and that uncertainty leaves modern cosmology in a strange position. Humanity possesses incredibly detailed knowledge about what happened shortly after the Big Bang. Scientists can model nuclear reactions in the early universe. They can calculate how hydrogen formed. They can predict cosmic background radiation with astonishing accuracy. But at the exact beginning itself, certainty dissolves. It is almost as if the universe hides its deepest origin behind a veil physics still cannot penetrate. Black holes may offer clues. Inside a black hole, matter collapses inward under extreme gravity. According to classical relativity, this process also leads toward a singularity. Time slows dramatically near the event horizon. Space becomes warped almost beyond recognition. Eventually, current equations again predict infinite density. But many physicists suspect something else happens before true infinity is reached. Quantum effects may intervene somehow. Hawking radiation, discovered by Stephen Hawking in the 1970s, revealed that black holes are not entirely black. Quantum processes near the event horizon allow them to slowly lose energy over unimaginable timescales. That discovery was revolutionary because it linked gravity, thermodynamics, and quantum mechanics together in unexpected ways. It hinted that black holes may contain hidden information about the deeper structure of reality itself. And this creates a fascinating possibility. The singularity at the beginning of the universe and the singularity inside black holes may not be separate mysteries. They may be connected symptoms of the same missing physics. Some researchers even speculate that new universes could emerge inside black holes. Others wonder whether our own universe might somehow be linked to processes occurring within a higher dimensional structure beyond observable reality. None of these ideas are proven. But the fact serious physicists explore them at all shows how incomplete humanity's current picture remains. There is something deeply cinematic about this stage of scientific discovery. Humanity standing at the edge of knowledge, staring into mathematical darkness where familiar reality dissolves. The stars above us look calm and eternal, but hidden beneath them lies evidence that the universe may rest on foundations stranger than ancient myths ever imagined. And perhaps the strangest part is this: singularities force science into philosophical territory, whether scientists want it or not. Because once time itself becomes unstable, ordinary questions stop behaving normally. What caused the Big Bang? Did something exist before it? Could causality itself emerge only after the universe cooled into a more stable state? These are no longer simple scientific questions. They become questions about whether the human concept of existence is even adequate for describing ultimate reality. The singularity may represent a true beginning, or it may represent the edge of human comprehension. Those are not the same thing. Somewhere beyond that wall of broken mathematics, something happened. Maybe a quantum fluctuation, maybe a cosmic bounce, maybe a transition from a previous state of reality that no longer resembles anything humans can visualize. Or perhaps reality simply does not obey the narrative structure human minds expect. Because the closer science approaches the first instant of existence, the more the universe stops looking like a machine and starts looking like something far stranger. A place where space can emerge, time can bend, and the laws of physics themselves may only be temporary features of a deeper cosmic order still hidden in darkness. For most of human history, nothing sounded simple. An empty room, a silent sky, a dark void without stars. The human mind naturally imagines emptiness as the absence of everything. No matter, no light, no movement, no sound, absolute nothingness. But the deeper modern physics explored reality, the more disturbing that idea became. Because, according to quantum theory, true emptiness may not actually exist anywhere in the universe. Even the vacuum of space, the cold darkness between galaxies, may be alive with invisible activity. And that changes the entire conversation about where the universe came from. When astronomers first began studying outer space centuries ago, they imagined the cosmos mostly as a giant emptiness scattered with stars. But by the 20th century, physics started uncovering something strange hidden underneath apparent nothingness. Empty space was not passive. It was not still. In some sense, it was restless. At the quantum level, reality behaves less like a machine and more like an unstable ocean, constantly trembling beneath the surface. Particles can appear briefly and disappear again. Energy fluctuates. Fields ripple invisibly through space, even in complete darkness. The vacuum itself contains activity that cannot be entirely removed. This sounds almost impossible at first, because human intuition was built around solid objects and visible motion. We expect something to come from something. We assume emptiness means the total absence of existence. But quantum mechanics repeatedly violates ordinary intuition in ways experiments continue confirming with astonishing precision. One of the reasons for this strange behavior lies in something called the uncertainty principle, developed by Werner Heisenberg in the 1920s. At microscopic scales, certain properties of particles cannot both be perfectly known at the same time. The more precisely one quantity is measured, the less certain another becomes. This uncertainty is not caused by poor instruments or human error. It appears woven into reality itself. And because of that uncertainty, quantum fields can never become perfectly still. Even at their lowest possible energy state, tiny fluctuations remain unavoidable. Space is never fully quiet, never fully frozen, never fully empty. Physicists call this the quantum vacuum. The name sounds misleading because the quantum vacuum is not nothing in the philosophical sense. It contains physical laws, fluctuating energy fields, and the potential for particles to emerge temporarily before vanishing again. Invisible pairs of particles and antiparticles can spontaneously appear from vacuum fluctuations, annihilate one another, and disappear almost instantly. These are often called virtual particles. Not virtual as in imaginary, but temporary. Fleeting disturbances inside quantum fields that normally vanish too quickly to observe directly. Yet their effects can still be measured indirectly in experiments. This is one of the reasons physicists take the quantum vacuum seriously. Its strange behavior is not merely mathematical fantasy. It leaves fingerprints on reality. One famous example is the Casimir effect. In simplified terms, two extremely close metal plates placed in a vacuum can experience a tiny force pushing them together because vacuum fluctuations behave differently in the narrow space between them than in the surrounding area. It is an eerie demonstration that empty space itself possesses measurable properties. And once scientists realized the vacuum was active rather than empty, a shocking possibility emerged. What if the universe itself originated from quantum fluctuations? Not from absolute philosophical nothingness, but from a quantum state where energy and physical laws already existed in some form. This idea remains controversial, partly because the word nothing becomes dangerously slippery. In everyday language, nothing means complete non-existence. But in quantum cosmology, nothing often refers to the absence of ordinary matter and classical space-time, not necessarily the absence of all physical structure. That distinction matters enormously. Because critics argue that a quantum vacuum is still very much something, it contains laws, fields, and mathematical behavior. Asking where those laws came from simply moves the mystery one step deeper rather than eliminating it. Still, the possibility remains fascinating because quantum mechanics allows events that classical physics would never permit. In ordinary life, objects require clear causes. A baseball moves because someone threw it. Fire exists because fuel ignited. But quantum systems behave probabilistically. Certain events occur without deterministic causes in the classical sense. Radioactive atoms decay unpredictably. Particles tunnel through barriers they seemingly should not cross. Reality at microscopic scales behaves less like a clock and more like shifting probabilities. Some physicists suspect the early universe may have emerged from similar quantum behavior. One of the most influential ideas connected to this is cosmic inflation. According to inflation theory, the universe experienced an unimaginably rapid burst of expansion during its earliest moments. Space expanded exponentially faster than the speed of light itself, smoothing out irregularities and creating the large-scale structure of the cosmos we observe today. Inflation helps explain why the universe appears remarkably uniform across enormous distances. It also explains subtle temperature variations observed in the cosmic microwave background radiation, ancient light left over from the early universe. But inflation introduces another deeply strange possibility. In some models, inflation may not stop everywhere at once. Certain regions of space stop inflating and form universes like ours, while other regions continue expanding indefinitely. This creates a scenario known as eternal inflation. And suddenly, reality becomes almost impossible to visualize. Imagine an infinite cosmic ocean constantly generating expanding bubbles. Each bubble becomes its own universe with its own stars, galaxies, and possibly even different physical laws. Our observable universe would be only one tiny region inside a much larger multiverse beyond direct observation. In this picture, quantum fluctuations are not minor background noise. They become the engines generating entire universes. Some physicists find this idea mathematically compelling. Others consider it deeply unsatisfying because it becomes difficult to test experimentally. But regardless of whether eternal inflation ultimately proves correct, it reveals how radically modern cosmology has transformed humanity's view of emptiness. The vacuum is no longer passive darkness. It may be creative. And that realization creates a strange emotional tension in physics. The closer scientists move toward explaining cosmic origins, the more unstable the concept of nothing becomes. Human language begins collapsing under the weight of ideas it was never designed to describe. Even the phrase, "before the universe," becomes dangerous territory, because time itself may emerge from the same underlying quantum processes. Some theoretical models suggest the universe could spontaneously tunnel into existence quantum mechanically. In certain interpretations, time may behave differently near the origin of the cosmos, perhaps even becoming more space-like than time-like under extreme conditions. Stephen Hawking once explored ideas suggesting the universe might not require a traditional beginning boundary at all. Using imaginary time in certain mathematical models, the universe could become finite, yet boundaryless, somewhat like the surface of Earth has no edge, even though it is limited in size. These ideas remain highly theoretical, but they reveal a deeper pattern running through modern cosmology. The universe may not have emerged from emptiness in the ordinary sense humans instinctively imagine. Instead, reality may arise naturally from deeper physical structures operating beneath classical space and time. There is something profoundly unsettling about that possibility, because human beings instinctively divide existence into categories: something versus nothing, beginning versus before, cause versus effect. But quantum physics repeatedly blurs those boundaries. The microscopic universe does not seem interested in preserving human common sense. And perhaps nowhere does this become stranger than in the energy hidden inside empty space itself. Some physicists believe vacuum energy may connect to dark energy, the mysterious phenomenon causing the expansion of the universe to accelerate today. Galaxies are not merely drifting apart from leftover momentum after the Big Bang. The expansion itself appears to be speeding up. Something woven into space may be driving it outward. Yet, when physicists attempt to calculate vacuum energy using quantum field theory, they encounter one of the greatest mismatches in scientific history. The predicted vacuum energy density becomes absurdly larger than what astronomers actually observe, off by an almost incomprehensible amount. It is as if modern physics glimpses part of a deeper truth, but cannot yet fully assemble the pieces together. And that uncertainty leaves open possibilities both exciting and terrifying. Maybe the quantum vacuum is the foundation beneath all universes. Maybe universes naturally emerge from fluctuating fields eternally. Maybe what humans call reality is only a temporary pattern rising from deeper quantum processes hidden underneath existence itself. Or maybe current theories remain incomplete in ways scientists do not yet understand. Because despite all the equations, all the particle accelerators, all the telescopes pointed into the darkness, one mystery remains stubbornly unresolved. Why does anything exist at all? Quantum theory may explain how particles fluctuate in empty space. It may explain how universes could emerge from unstable quantum states. But it does not fully explain why the laws themselves exist, why quantum fields exist, or why reality allows existence instead of permanent silence. And perhaps that is why the quantum vacuum feels so haunting to think about. It transforms emptiness into something active and alive. Yet it also pushes the ultimate mystery farther away. Every answer uncovers another deeper layer beneath it. The ancient human fear of the void came from imagining absolute darkness and absence. Modern physics replaced that darkness with something arguably stranger, an invisible sea of restless energy where particles flicker into existence, where universes may emerge from fluctuations, and where the line between nothing and something may never have been as clear as humanity once believed. Somewhere beneath all matter, beneath all stars, beneath every galaxy drifting through the cosmic night, the vacuum continues trembling quietly. And inside those fluctuations may lie the first hidden heartbeat of the universe itself. There is a strange pattern hidden almost everywhere in nature. Hearts contract and expand. Lungs inhale and exhale. Oceans rise and fall beneath the moon. Seasons cycle endlessly through warmth and cold. Even stars are born, evolve, collapse, and scatter their remains back into space where new stars eventually form again. For thousands of years, human civilizations looked at these repeating rhythms and wondered whether the universe itself might also move in cycles. Not a single beginning followed by eternal expansion, but an endless cosmic breathing. Creation followed by collapse. Collapse followed by rebirth. Modern cosmology once seemed to destroy that possibility. When 20th century astronomers discovered that galaxies were moving apart, it appeared the universe had started from a single explosive origin and had been expanding ever since. The Big Bang became the dominant explanation because evidence supported it so strongly. Space itself was stretching. Ancient radiation filled the cosmos. Galaxies were receding in every direction. But hidden beneath that success remained an unsettling question. Would the expansion continue forever? Or could gravity eventually reverse everything? For decades, scientists seriously considered the possibility that the universe might someday stop expanding and begin collapsing inward. If enough matter existed, gravity could potentially overpower expansion over immense timescales. Galaxies would slowly drift closer together. Temperatures would rise. Space would contract. Eventually, all matter could collapse back toward an ultra-dense state in an event sometimes called the Big Crunch. And if that happened, another question immediately emerged. What if the collapse triggered another Big Bang? What if our universe was only one phase in an endless sequence of cosmic cycles? This idea became known in various forms as the oscillating universe or cyclic universe model. Instead of reality beginning once and only once, the cosmos might repeatedly die and regenerate forever. There is something deeply haunting about that possibility, because it transforms the universe from a single event into a rhythm without a clear beginning or end. Entire galaxies would become temporary. Stars, planets, civilizations, all part of recurring cosmic eras, separated by unimaginable stretches of time. At first glance, the idea almost feels poetic rather than scientific. But physics eventually discovered reasons to take certain cyclic models seriously. One problem came from the singularity itself. If the universe truly began from infinite density, physics breaks down completely. But some researchers wondered whether the singularity might be avoidable if the universe never actually reached infinite compression. Maybe the collapse stops at extremely small scales because quantum effects intervene before true infinity occurs. This is where newer theories entered the story. Loop quantum gravity, one of the major approaches to quantum gravity, proposes that space-time itself may have a discrete microscopic structure rather than being perfectly continuous. Under certain versions of the theory, compression eventually encounters a kind of quantum resistance. Space cannot shrink indefinitely, and suddenly, a radical possibility appears. Instead of collapsing into a singularity, a dying universe might rebound outward, a bounce. Not an absolute beginning, but a transition. In these models, the Big Bang becomes less like a creation event and more like the aftermath of a previous cosmic phase. The universe before ours contracts inward over billions or even trillions of years until quantum gravitational effects become dominant. Then, instead of collapsing into infinite density, space-time rebounds outward again, creating a new, expanding universe, a big bounce. The idea changes the emotional feeling of cosmology completely. The universe no longer resembles a story with a single opening chapter. It becomes more like an endless ocean tide, moving through cycles too enormous for human minds to naturally grasp. And strangely enough, some versions of these theories solve certain problems rather elegantly. Standard Big Bang cosmology struggles with questions about why the universe began in such a low entropy, highly ordered state. Entropy, in simple terms, measures disorder. Normally, systems become more disordered over time. Ice melts, structures decay, energy spreads out. Yet the early universe appears to have started remarkably smooth and ordered, despite containing immense energy. Cyclic models attempt to explain this by proposing that each cosmic cycle resets certain conditions. Some versions suggest entropy could be diluted during periods of expansion, or transformed in ways not fully understood yet. Others imagine entirely different mechanisms operating during contraction phases. None of these ideas are universally accepted, but they remain active areas of research precisely because the singularity problem still haunts cosmology. And then there are the darker possibilities. If the universe truly cycles forever, what happens to information from previous universes? Does anything survive? Could traces from earlier cosmic eras remain hidden somewhere inside ours? Some researchers have explored whether unusual patterns in the cosmic microwave background radiation might contain hints of pre-Big Bang physics. Most evidence remains inconclusive, but the search itself reveals something remarkable. Modern science has reached the point where it seriously investigates whether another universe existed before ours. That idea would have sounded almost mystical centuries ago. Now it appears in peer-reviewed cosmology papers. One particularly fascinating version of cyclic cosmology emerged from string theory and higher dimensional physics. In certain models, our observable universe may exist on a vast, membrane-like structure called a brane, floating inside a higher dimensional reality. According to the ekpyrotic model, the Big Bang was not the ultimate beginning, but the result of a collision between enormous, higher dimensional branes. When these structures interact, immense energy releases into space, creating conditions resembling a Big Bang. In this picture, universes can repeatedly emerge through cycles of collision and separation. The implications become almost impossible to visualize. Human beings naturally imagine the universe as everything that exists. But these theories suggest our cosmos may only be a thin slice inside a far larger structure hidden beyond ordinary perception. Not another galaxy, not another universe far away in space, a deeper level of reality entirely. And yet, despite how exotic these ideas sound, they arise from serious attempts to solve real mathematical problems in cosmology. Scientists are not inventing cosmic cycles simply because they are philosophically attractive. They are trying to repair places where current physics breaks apart. Still, observations have complicated the picture. In the late 1990s, astronomers discovered something shocking while studying distant supernovae. The expansion of the universe was not slowing down as many expected. It was accelerating. Some unknown force, now called dark energy, appears to be pushing space apart faster over time. This discovery dramatically altered discussions about the universe's future. If expansion accelerates forever, a future collapse may never occur. Galaxies could drift endlessly farther apart until the night sky itself becomes dark and empty beyond local cosmic neighborhoods. In that scenario, the universe may slowly fade toward a cold, dilute future, sometimes called heat death. But even dark energy remains deeply mysterious. Nobody fully understands what it is. Some physicists wonder whether dark energy itself could evolve over time. Others speculate the acceleration might eventually reverse under conditions not yet understood. Cosmology remains full of uncertainty because the universe consistently behaves in ways more complex than expected. And this uncertainty keeps cyclic models alive. Not proven, not dominant, but not dead either. There is something psychologically strange about contemplating eternal cosmic cycles. Human beings instinctively think in linear narratives: birth, life, death, beginning, end. But a cyclic universe removes the comfort of a final starting point. It replaces creation with recurrence. Imagine standing beneath a night sky, knowing every galaxy above you may have existed before in another form. That stars may have burned in earlier cosmic ages, long before our universe emerged. That space itself could be participating in rhythms spanning eternity. The mind almost resists the idea because human life is so brief by comparison. Civilizations rise and disappear in mere thousands of years. Species evolve across millions. But cosmic cycles, if they exist, may unfold across timescales so enormous they nearly erase the distinction between physics and mythology. And perhaps that is why the concept remains so captivating, because it touches something ancient inside human imagination while still emerging from modern mathematics. The universe expanding forever from a single beginning feels vast already, but an eternal sequence of universes collapsing and rebounding stretches the imagination into something even more unsettling. No absolute first moment, no final ending, only transitions. Some physicists caution that cyclic models still face serious problems. Certain versions struggle with entropy buildup across repeated cycles. Others depend on speculative physics not yet experimentally verified. The evidence today does not conclusively prove that our universe emerged from a previous one. But neither has science fully ruled the possibility out. And that lingering uncertainty matters, because it means humanity still does not know whether the Big Bang was truly the beginning of existence or simply the latest visible chapter in a much older cosmic process hidden behind the limits of current understanding. Somewhere beyond the observable horizon, beyond ancient radiation, beyond the edge where known physics begins dissolving into uncertainty, the universe may carry memories of earlier realities we cannot yet access. Or perhaps the cosmos really did emerge only once. Right now, science cannot say for certain. But the fact that modern physics even allows room for such possibilities reveals how strange reality has become at its deepest levels. The universe no longer looks static, mechanical, or simple. It looks dynamic, evolving, potentially recursive, almost alive in its own enormous way. And if the cosmos truly breathes through endless cycles of expansion and collapse, then somewhere in the unimaginable future, long after every star in our sky has died, long after galaxies themselves have faded into darkness, space may once again begin falling inward toward another impossible moment, another compression beyond comprehension, another rebirth, another dawn for a universe that has already forgotten how many times it has existed before. When people first realized the universe was expanding, the discovery already felt enormous enough to reshape humanity's place in existence. The cosmos was not static. Space itself was stretching. Galaxies were drifting apart like fragments carried outward by an invisible tide. But over time, a far stranger possibility slowly emerged from the mathematics. One so unsettling that even some physicists remain uncomfortable discussing it openly. What if our universe is not the universe? What if the Big Bang was not the beginning of everything, but only the birth of one isolated region inside something vastly larger? A single bubble in an endless cosmic sea. At first, the idea sounds more like science fiction than science. Human beings naturally think of the universe as all of reality. By definition, nothing should exist outside it. But modern cosmology has repeatedly forced science to abandon intuitive assumptions, and the deeper researchers explored the early universe, the more certain equations began hinting toward something extraordinary. our observable cosmos may not be unique at all. The path toward this idea began with a problem. When astronomers studied the large-scale structure of the universe, they discovered something oddly precise about it. Space appears remarkably smooth across enormous distances. Regions billions of light years apart contain nearly the same average temperature and density. That sounds ordinary until you realize those regions should never have had enough time to exchange information or energy with one another after the Big Bang. According to ordinary expansion alone, distant parts of the universe should look far more uneven, yet they do not. To explain this mystery, physicists proposed a dramatic idea in the early 1980s called cosmic inflation. According to the theory, the universe underwent an unimaginably rapid expansion during its earliest moments, faster than the speed of light itself. Tiny microscopic regions suddenly ballooned into cosmic scales almost instantly. Inflation solved several major cosmological puzzles with remarkable elegance. It explained why the universe appears flat, smooth, and geometrically stable across immense distances. Over time, evidence from the cosmic microwave background radiation strengthened support for inflationary models. But inflation introduced a dangerous implication. Once physicists studied the equations carefully, they realized inflation might not stop everywhere at the same time. In some versions of the theory, space continues inflating eternally in the background, while localized regions stop inflating and form universes like ours. These regions become isolated bubble universes, surrounded by rapidly expanding space beyond direct observation. And suddenly, the scale of reality changes completely. The observable universe, all the galaxies humanity can ever see, may be only one microscopic pocket inside a much larger structure beyond comprehension. An endless multiverse. The imagery almost feels biological. Tiny universes budding from a larger cosmic environment, like bubbles forming in boiling water. Each one expanding independently. Each one potentially containing different histories, different structures, perhaps even different laws of physics. Some universes might collapse almost immediately after forming. Others may expand too rapidly for stars to ever emerge. In some, gravity could be weaker. In others, chemistry might never stabilize enough for planets or life to exist at all. And somewhere among these countless possibilities exists one universe where human beings evolved to stare upward and wonder how reality began. There is something deeply unsettling about that idea, because it removes the sense of cosmic specialness humans instinctively search for. For centuries, people assumed Earth occupied the center of creation. Then, astronomy revealed Earth orbited the Sun. Later discoveries showed the Sun was only one ordinary star among hundreds of billions inside the Milky Way. Then, the Milky Way itself became one galaxy among trillions. The multiverse pushes that demotion even further. Not only may humanity be insignificant within the universe, our entire universe may itself be only one tiny region inside a much larger cosmic system. And strangely enough, some physicists believe this possibility could explain one of the greatest mysteries in science: why the laws of physics appear so finely tuned for complexity and life. The constants governing reality seem delicately balanced. If gravity were slightly stronger or weaker, stars might not form properly. If certain subatomic forces changed slightly, chemistry could collapse. Even tiny alterations to fundamental constants might produce sterile universes filled only with radiation or dead matter. This apparent fine-tuning has puzzled scientists for decades. Some interpret it philosophically or spiritually. Others search for deeper physical explanations. But within the multiverse framework, the puzzle changes dramatically. If countless universes exist with varying properties, then naturally, some rare regions would accidentally possess conditions compatible with galaxies, stars, planets, and observers. Human beings would only ever appear in one of those rare universes, because observers cannot emerge where conditions forbid complexity. This reasoning is known as the anthropic principle, and it remains deeply controversial. Critics argue it risks becoming scientifically unsatisfying because it explains fine-tuning statistically rather than through deeper mechanisms. Supporters counter that the multiverse may simply be the unavoidable consequence of inflationary physics, whether humans like the implications or not. And that tension runs through nearly every multiverse discussion. The mathematics can appear compelling, but experimental evidence remains elusive. Because if other universes exist outside our observable region, reaching them may be fundamentally impossible. Space between bubble universes could expand faster than light indefinitely, permanently isolating them from one another. The multiverse might therefore remain scientifically frustrating, potentially real, yet partially inaccessible. Still, scientists continue searching for indirect clues. Some researchers have proposed that collisions between bubble universes in the distant past could leave subtle scars in the cosmic microwave background radiation. Others investigate whether fundamental constants show signs of deeper underlying structures predicted by multiverse-related theories. So far, nothing conclusive has emerged. Yet the idea refuses to disappear, because modern physics repeatedly leads back toward it from multiple directions. String theory added another layer to the story. In many string theory models, the number of possible vacuum states becomes enormous, perhaps unimaginably enormous. Different configurations of extra dimensions could produce different physical laws, particle types, and constants. Instead of one inevitable universe, reality may allow an immense landscape of possible universes. This concept became known as the string landscape. And suddenly, the multiverse no longer appeared as a speculative side idea. It started looking like a natural consequence of several major theoretical frameworks simultaneously. Inflation suggested endlessly spawning universes. String theory suggested enormous numbers of possible physical realities. Quantum mechanics introduced additional bizarre possibilities of its own. Some interpretations of quantum theory, particularly the many worlds interpretation proposed by Hugh Everett in the 1950s, suggest reality may continuously branch into multiple quantum histories whenever probabilistic events occur. In this picture, every quantum possibility actually happens, but in separate branches of reality. A particle decays and does not decay. A choice occurs one way and another way simultaneously across different branches. Entire histories split continuously. Not everyone accepts this interpretation, and it remains philosophically divisive. But it reveals something extraordinary about modern physics. multiple independent areas of science now hint toward realities larger and stranger than the single visible universe humans once assumed existed. And psychologically, the implications become difficult to absorb. Imagine standing beneath a clear night sky, realizing every visible star already feels impossibly distant. Then, imagine those stars themselves existing inside only one universe among perhaps infinitely many others, forever beyond observation. The scale becomes almost emotionally destabilizing. Human beings evolved to navigate forests, storms, rivers, predators, and social groups. Our brains were never built to intuitively process infinities of universes. Yet, modern cosmology increasingly pushes thought into those territories anyway. Some scientists remain skeptical of multiverse theories precisely because they challenge traditional ideas about testability. Physics normally depends on observation and prediction. If other universes cannot be directly observed, critics argue the concept risks drifting toward metaphysics. Others respond that if established theories mathematically predict multiverses while also successfully explaining observable phenomena, then ignoring the implications would itself be unscientific. The debate remains unresolved. And perhaps that uncertainty is exactly what makes the multiverse so haunting. Because, unlike ancient myths, these ideas do not emerge from pure imagination. They emerge from equations built to explain real observations about cosmic expansion, quantum mechanics, and fundamental physics. The mathematics itself seems to whisper that reality may be larger than the visible cosmos. Whether humanity ultimately proves the multiverse exists or not, the idea has already transformed the philosophical landscape of science. The universe no longer appears simple, singular, or comfortably understandable. It appears layered, potentially infinite, structured in ways human intuition struggles to visualize. And somewhere beyond the observable horizon, beyond the oldest light in existence, beyond every galaxy humanity will ever see, there may be countless other universes drifting forever through inaccessible darkness. Some may be empty. Some may burn briefly and die. Some may contain stars under unfamiliar laws of physics. And in at least one of them, perhaps another civilization is also staring into the night sky, wondering whether their universe is the only one that exists, never realizing they too may simply be living inside another temporary bubble, floating through a far greater reality, hidden beyond the edge of everything they can ever observe. Every human life is built around time. You wake up in the morning because clocks tell you morning exists. Your memories stretch backward into childhood. Your thoughts move forward into tomorrow. You age second by second without ever choosing to. Time feels so natural, so unavoidable, that most people never stop to question whether it is truly real in the way we assume. But modern physics has quietly uncovered something deeply unsettling. The universe does not experience time the way human beings do, and at the deepest levels of reality, time itself may not even exist at all. That idea sounds impossible at first, because human consciousness is almost inseparable from the sensation of time passing. Every emotion depends on it: fear, hope, regret, anticipation. Even identity depends on remembering a past version of yourself and imagining a future one. Remove time completely, and ordinary human experience begins to collapse into something almost impossible to describe. Yet the deeper science explored the cosmos, the stranger time became. For most of history, people assumed time flowed universally across the universe like an invisible cosmic river. 1 second on Earth was 1 second everywhere else. The future moved steadily forward for all things equally. Then, Albert Einstein shattered that assumption forever. In 1905, Einstein introduced special relativity, revealing that time is not fixed or universal. It stretches and slows depending on motion. Two observers moving differently through space can experience time differently. Clocks traveling at high speeds tick more slowly compared to clocks at rest. At first, this sounded absurd even to scientists, but experiments repeatedly confirmed it. Atomic clocks flown aboard airplanes measured tiny but real differences compared to clocks left on Earth. Satellites orbiting our planet must constantly adjust for relativistic time distortions, or GPS systems would fail. Reality itself does not maintain one universal clock, and Einstein's later theory of general relativity pushed the idea even further. Gravity affects time. Near massive objects, time slows down. The stronger the gravity, the slower clocks move relative to distant observers. Near a black hole, the effect becomes extreme. Someone watching from far away could see time near the event horizon almost freezing. This is not illusion. It is physical reality, which means time is not separate from the universe. It is woven into the structure of space itself, flexible, distortable, influenced by energy and gravity. And once physicists realized time could bend, another terrifying possibility emerged. What if time is not fundamental at all? What if it only appears real under certain conditions? Some of the strangest clues come from attempts to unite quantum mechanics with gravity. The equations describing the microscopic world behave very differently from those describing space-time on cosmic scales. And when physicists attempt to merge them into one deeper theory, time begins behaving in unexpected ways. One famous example appears in an equation known as the Wheeler-DeWitt equation, developed in attempts to describe quantum gravity. What shocked physicists about the equation was not only its complexity, it was the apparent absence of time. The equation describing the quantum state of the universe does not contain time in the ordinary sense humans expect. At the deepest level, reality may not evolve moment by moment the way daily experience suggests. Instead, the universe may exist more like a complete structure where past, present, and future are not fundamentally separate. This idea sometimes connects to what physicists and philosophers call the block universe. In this picture, time does not flow. Instead, all moments exist simultaneously within space-time. The past still exists. The future already exists. Human consciousness simply experiences reality sequentially, moving through moments one after another, like a flashlight sweeping across an already complete landscape. The implications become psychologically disturbing almost immediately. If the block universe interpretation reflects reality, then the future may in some sense already exist, even though humans cannot perceive it yet. Every conversation, every war, every extinction, every birth, every final moment of humanity may already occupy coordinates within space-time. Not predetermined in the simplistic sense of destiny, perhaps, but existing within the geometry of reality itself. And strangely enough, relativity partially supports this unsettling picture. Different observers moving relative to one another disagree about which events happen now. There is no universal present moment shared across the cosmos. What counts as simultaneous depends on perspective. Human intuition hates this. The brain craves a moving present, a dividing line between a fixed past and an open future. But physics increasingly suggests that division may not be fundamental to reality itself. Then, quantum mechanics complicates everything even further. At microscopic scales, particles exist in states of probability until interactions occur. Some interpretations suggest the future remains genuinely indeterminate until quantum events unfold. Others argue all possible outcomes coexist simultaneously in branching quantum realities. And suddenly, science finds itself trapped between two radically different visions of time. Relativity suggests the universe may already exist as a complete space-time structure. Quantum mechanics suggests uncertainty and probability remain deeply woven into reality. Physicists still do not fully know how to reconcile these pictures. But the mystery grows even stranger when thermodynamics enters the story. Human beings experience time as moving in one direction because entropy increases. Ice melts, stars burn fuel, structures decay, eggs break, but do not spontaneously reassemble. The universe naturally evolves from ordered states toward greater disorder. This progression creates what scientists call the arrow of time. But fundamental physical laws themselves are often time-symmetric. At microscopic levels, many equations work almost equally well forward or backward in time. The deep laws of physics do not strongly prefer past over future. So why does time appear directional to us? Some physicists argue the answer lies in the extraordinarily low entropy conditions of the early universe. The cosmos began in an unusually ordered state, allowing entropy to increase afterward and creating the sense of temporal flow humans experience. But this explanation raises another profound mystery. Why did the universe begin in such an ordered state at all? No one fully knows, and hidden inside that uncertainty is a disturbing possibility. The flow of time humans experience may emerge from statistical behavior rather than fundamental reality. In other words, time may resemble temperature. Temperature feels real in daily life, yet it emerges from microscopic particle motion rather than existing as a separate substance itself. Similarly, the sensation of time flowing may emerge from deeper processes rather than being a basic ingredient of the universe. Some theoretical physicists now seriously explore models where space and time themselves emerge from more fundamental quantum relationships beneath ordinary reality. This means the universe at its deepest level may not contain clocks ticking through moments at all. Instead, time could arise only within certain large-scale structures, an illusion generated by information, entropy, and consciousness interacting together. There is something deeply eerie about this possibility because it destabilizes nearly every instinct humans possess about existence. Imagine looking at a family photograph from years ago. The people in the image seem trapped permanently in the past. But within the block universe interpretation, those moments may still exist in space-time, just as physically as the present moment you occupy now. Your childhood may still exist. Ancient Rome may still exist. The first stars may still burn somewhere within the geometry of space-time, not accessible to us, but not erased either. And if time truly emerges, rather than fundamentally exists, then the question, what happened before the Big Bang, becomes even stranger than it first appeared. Because before itself may only make sense after time emerges. Some cosmologists suspect the earliest universe existed in a state where ordinary temporal distinctions break down completely. Near the Planck scale, where quantum gravity dominates, space and time may blur together into something more primitive and unfamiliar than human language can easily describe. This is one reason certain physicists argue asking what came before the Big Bang may resemble asking what lies north of the North Pole. The structure of the question itself could become meaningless once time ceases functioning normally. Yet not everyone accepts this conclusion. Some researchers continue exploring cyclic cosmologies, eternal inflation, quantum bounce models, or hidden dimensions where time may extend beyond the Big Bang in unfamiliar ways. Others suspect human understanding of time remains profoundly incomplete. And honestly, that uncertainty may be the most important part of the entire mystery. Because, despite all modern physics has discovered, nobody truly understands why conscious beings experience reality as moving through time at all. Science can describe clocks, entropy, relativity, quantum probabilities, but subjective temporal experience, the sensation of now slipping endlessly forward, remains one of the strangest features of existence. The universe may not contain an objective present. The future may already exist in some form. Time itself may emerge from deeper structures beneath reality. Or human intuition may still be missing something fundamental. Right now, no one can say with certainty, but one thing has become increasingly clear. Time is far stranger than humanity once believed. It bends, slows, distorts, possibly emerges, perhaps even disappears under extreme conditions. And somewhere, beneath the movement of galaxies, beneath the ticking of clocks, beneath every memory and every future hope carried through human lives, reality may exist in a state where time itself, the thing that seems most unavoidable in all existence, is not truly fundamental at all, but only a temporary feature of a universe still hiding its deepest structure in darkness. At some point, every explanation about the origin of the universe runs into the same terrifying question. What actually triggered the Big Bang? Not what happened after it. Science can describe that part surprisingly well. Physicists can reconstruct how the early universe cooled, how particles formed, how hydrogen emerged, how gravity shaped galaxies, and how stars eventually ignited across cosmic darkness. But when the story moves closer to the beginning itself, the certainty starts fading. Because even if the universe expanded from an extremely hot and dense state, something still seems missing. Why did it happen at all? What pushed reality into motion? For centuries, human beings imagined creation as a single dramatic event, a divine command, a cosmic spark, a moment when existence suddenly erupted from silence. Modern science replaced mythology with mathematics, but the emotional mystery never disappeared. It only became stranger. The deeper physics investigates the beginning of the universe, the less the Big Bang resembles an ordinary explosion, and the more it resembles a transition from a state humanity still does not fully understand. And hidden inside that uncertainty are some of the most radical ideas modern science has ever considered. One possibility is that nothing triggered the Big Bang in the ordinary sense at all. In quantum mechanics, events do not always require causes the way classical intuition expects. At microscopic scales, reality behaves probabilistically. Particles fluctuate. Radioactive atoms decay unpredictably. Certain quantum events occur without deterministic triggers visible inside the equations. This has led some physicists to wonder whether the universe itself could have emerged as a quantum event, not from absolute philosophical nothingness, but from a quantum state capable of fluctuating spontaneously. In some models, the vacuum of space is never perfectly empty. Quantum fields continue fluctuating even in their lowest energy states. Tiny disturbances constantly appear and disappear. Usually, these fluctuations are microscopic and temporary. But under extreme conditions, some researchers propose a fluctuation could trigger rapid cosmic inflation, a runaway expansion producing an entire universe. And suddenly, the Big Bang no longer looks like a carefully planned beginning. It starts resembling a spontaneous instability in reality itself. That possibility feels deeply unsettling because human minds instinctively expect ultimate explanations to feel stable and intentional. But quantum physics repeatedly suggests that uncertainty may be woven into existence at the deepest levels. Still, quantum fluctuations alone do not fully solve the mystery, because another question immediately appears beneath them. Where did the quantum vacuum come from? Why do quantum laws exist at all? What framework allowed fluctuations to happen in the first place? And once again, the mystery moves one layer deeper. Some physicists instead explore the possibility that the Big Bang was triggered by a transition from a previous cosmic state. This idea becomes especially important in cyclic or bounce cosmologies. If another universe existed before ours, the Big Bang may not have been an absolute origin, but the result of a collapse and rebound process. As a previous universe contracts under gravity, densities and energies rise toward extreme conditions. Quantum gravitational effects may eventually halt the collapse and reverse it outward into expansion. A bounce. In this picture, the Big Bang becomes less like a creation event and more like a transformation. One universe dying into another. The emotional feeling of this idea is almost eerie because it removes the comfort of a single beginning. Reality becomes recursive, eternal in some form. Universes giving birth to future universes across unimaginable stretches of time. And strangely, certain mathematical models allow this possibility surprisingly naturally. Loop quantum gravity, for example, suggests space-time itself may possess a discrete microscopic structure. Instead of compressing infinitely, space eventually resists total collapse at quantum scales. The singularity disappears, replaced by a bounce between contracting and expanding phases. But even here, uncertainty remains enormous. No experiment has yet confirmed what truly happens under such extreme conditions. The energies involved lie far beyond anything humanity can recreate in laboratories. Physicists are trying to understand the origin of existence itself using incomplete theories stitched together from fragments of observable evidence. And that limitation matters, because it means modern cosmology is navigating the edge between known science and deep speculation. Then there are the even stranger possibilities emerging from higher dimensional theories. In some versions of string theory, the universe we inhabit may exist on a vast membrane-like structure called a brain, floating through a higher dimensional space. According to certain models, the Big Bang occurred when enormous brains collided with one another. The collision released tremendous energy into our universe, generating matter, radiation, and expansion. What makes this idea so unsettling is that it transforms the Big Bang from an isolated event into something almost mechanical within a larger, hidden reality. Universes could repeatedly emerge through interactions between higher dimensional structures humans cannot directly observe. Imagine living inside a two-dimensional world painted on the surface of a sheet of paper, completely unaware that gigantic objects exist beyond your dimensions. Then one day, the sheet collides with another hidden surface, releasing enormous energy throughout your entire reality. To beings trapped inside the sheet, the event would appear cosmic and absolute. But from a higher dimensional perspective, it might simply be one interaction among many. This is part of what makes modern cosmology feel increasingly surreal. The universe no longer appears self-contained or intuitively understandable. Every attempt to explain the Big Bang opens larger frameworks behind it: hidden dimensions, quantum fluctuations, multiverses, cyclic realities. And with each new layer, the original question becomes more difficult rather than less. Because ultimately, humanity is still trying to answer something ancient. Why is there something instead of nothing? Some physicists argue the question itself may be flawed. Perhaps reality does not require an ultimate trigger in the way human intuition assumes. Causality itself depends on time, and if time emerged alongside the Big Bang, then asking what caused the Big Bang may resemble asking what happened before North existed. This perspective appears in several quantum cosmology models, where ordinary time loses meaning near the beginning of the universe. Instead of a classical starting point, reality may transition smoothly through quantum states, where distinctions between before and after become physically meaningless. Stephen Hawking famously explored ideas suggesting the universe might be finite but boundaryless. In certain mathematical descriptions, asking what came before the Big Bang becomes similar to asking what lies south of the South Pole. The geometry simply does not contain such a direction. Yet, many scientists remain cautious about fully embracing this conclusion because the human mind resists abandoning causality so completely. Intuition constantly searches for prior explanations. Every event in ordinary life emerges from earlier conditions. But ordinary life evolved inside a calm, low-energy environment on a small rocky planet, not inside the birth conditions of the universe itself. And perhaps that is part of the problem. Human cognition may simply be too limited to naturally understand cosmic origins. Some researchers openly acknowledge this possibility. The brain evolved for survival, not for comprehending quantum gravity or higher dimensional cosmology. Our intuitions about beginnings, causes, and time may function well at human scales while failing completely near the foundations of reality. There is something strangely humbling about that realization. For centuries, humanity assumed science would eventually explain everything cleanly and completely. But modern cosmology increasingly reveals layers of mystery beneath every answer. The closer physics moves toward the origin of existence, the more reality starts behaving unlike anything human beings evolved to imagine. And perhaps nowhere is that clearer than in inflation theory itself. Inflation suggests the universe expanded exponentially fast during its earliest moments, smoothing space into the remarkably uniform cosmos we observe today. But some versions of inflation become eternal. Inflation never fully ends everywhere. Instead, localized regions stop inflating and form universes like ours, while expansion continues elsewhere indefinitely. This means our Big Bang may not have been unique. It may simply mark the formation of one bubble universe inside a much larger, inflating background. And if that is true, then the trigger for our Big Bang might not have been a singular cosmic event at all. It could have been one localized transition among countless others, occurring endlessly throughout a larger multiversal structure. The implications become emotionally overwhelming very quickly. Entire universes forming continuously beyond observation. Different laws of physics, different histories, infinite cosmic landscapes forever inaccessible from our own bubble of reality. And somewhere inside all of it, humanity trying to understand why existence exists. What makes this search so compelling is that every proposed trigger for the Big Bang reveals something profound about the universe itself. If the cosmos emerged from quantum fluctuations, reality may be fundamentally probabilistic. If it emerged from a bounce, existence may be cyclic. If higher dimensional collisions created it, the universe may be only one layer inside a far greater structure. If time itself began with the Big Bang, then causality may not apply to cosmic origins at all. Each possibility reshapes humanity's understanding of existence, and yet none of them are fully proven. That uncertainty frustrates some people, but in another sense, it may be one of the most beautiful aspects of modern cosmology. Humanity has reached a point where science no longer merely maps stars and planets. It confronts the deepest structure of reality itself. The questions have become enormous, not simply where galaxies came from, but why anything exists at all. Somewhere beyond the first measurable instant of cosmic history, beyond quantum foam, beyond inflation fields and singularities and higher dimensional collisions, something happened, or perhaps something always was. Right now, no equation can say for certain. But the fact that the universe exists at all, that stars formed, that atoms organized into living minds capable of asking these questions, may itself be one of the strangest outcomes in all of reality. Because whatever triggered the Big Bang did not merely create matter and energy, it eventually created observers capable of staring back into the darkness and wondering how the entire story ever began. there is something almost impossible about what humanity is trying to do. A species that evolved on a small, rocky planet beneath the light of one ordinary star is attempting to look backward through space and time toward the beginning of reality itself. Not metaphorically, literally. Modern telescopes are machines built to peer into the past because light takes time to travel. Every distant galaxy appears not as it is now, but as it once was. The farther we look into space, the deeper we look into cosmic history. And eventually, if we look far enough, we approach the edge of visible creation. The strange thing is that ancient humans once believed the heavens were unreachable, permanent lights fixed above Earth. Today, humanity launches instruments beyond the atmosphere capable of detecting radiation older than galaxies, measuring invisible distortions in space-time, and observing light that began traveling before Earth even existed. But despite all this progress, there remains a wall no telescope has fully crossed. A boundary near the beginning of the universe where visibility itself breaks down. And scientists are obsessed with trying to see beyond it. The reason begins with light. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense. Matter did not exist in stable forms. Atoms had not formed yet. Space was filled with an opaque plasma of charged particles and radiation colliding constantly. Light could not travel freely because photons scattered endlessly through the chaos. The young universe was not dark. It was too bright to see through. Then, roughly 380,000 years after the Big Bang, temperatures finally cooled enough for electrons and atomic nuclei to combine into neutral atoms. Suddenly, radiation could move freely across space. The universe became transparent for the first time. That ancient light still exists today. It fills the cosmos faintly in every direction as the cosmic microwave background radiation, a weak afterglow from the early universe itself. When scientists discovered this radiation in 1965, it transformed cosmology forever. For the first time, humanity possessed direct observational evidence of the universe's ancient past. The microwave background became a kind of fossil light, preserving information about conditions long before stars or galaxies formed. But it also revealed a frustrating limit. No ordinary light can show us what happened earlier than that era, because before transparency emerged, radiation remained trapped inside the plasma. The universe hides its earliest moments behind a glowing curtain. And that means scientists must search for other clues. One method involves studying tiny temperature variations hidden inside the cosmic microwave background itself. Although the radiation appears remarkably uniform, extremely subtle fluctuations exist across the sky, differences smaller than a fraction of a degree. Those tiny irregularities matter enormously. They represent ancient density fluctuations from the early universe, the seeds that gravity later transformed into galaxies, stars, and planets. In some sense, every galaxy visible today grew from microscopic ripples frozen into the young cosmos billions of years ago. Experiments like COB, E, WM, A, P, and the Planck satellite mapped these fluctuations with astonishing precision. Their observations strongly supported inflation theory, the idea that the universe underwent a brief period of exponential expansion shortly after the Big Bang. But scientists hoped for even more. If inflation truly occurred, it may have generated primordial gravitational waves, faint ripples in space-time itself, stretching across the newborn universe. Detecting those waves could reveal information from unimaginably early moments, potentially closer to the beginning than any light-based observation can reach. And for a moment, humanity thought it had succeeded. In 2014, researchers from the BICEP 2 experiment announced evidence suggesting they had detected patterns in cosmic radiation potentially caused by primordial gravitational waves from inflation. Headlines exploded across the world. Some believed humanity had glimpsed echoes from the birth of the universe itself. Then, the excitement collapsed. Further analysis revealed much of the signal could be explained by interstellar dust within our galaxy. The discovery became a painful reminder of how difficult cosmology truly is. Scientists are attempting to reconstruct the origin of reality using faint whispers buried beneath cosmic noise billions of years old. Still, the search continues. Because if primordial gravitational waves are eventually confirmed, they could reveal conditions from fractions of a second after the Big Bang, long before ordinary matter existed. And that possibility changes the emotional scale of astronomy completely. Humanity is no longer merely observing stars. It is trying to reconstruct the first moments of existence itself. The James Webb Space Telescope added another layer to this search. Webb was designed partly to study the early universe by observing extremely distant galaxies whose light traveled for over 13 billion years before reaching Earth. When its first deep-field images arrived, they stunned astronomers. Ancient galaxies appeared larger, brighter, and more developed than many models predicted. Entire galactic structures seemed to emerge surprisingly early in cosmic history. Scientists are still debating what these observations ultimately mean. Some interpretations may require revisions to current galaxy formation models. Others caution against drawing dramatic conclusions too quickly. But once again, the universe reminded humanity of something unsettling. Every time science believes it understands the cosmos clearly, reality reveals another layer of complexity underneath. And this pattern repeats constantly in cosmology. The closer humans try to move toward the beginning, the stranger the universe becomes. Some researchers now search for signs that our universe may have collided with another universe in the distant past. If bubble universes exist within a multiverse framework, ancient collisions could potentially leave circular scars or unusual asymmetries in the cosmic microwave background radiation. So far, evidence remains inconclusive, but the fact serious scientists investigate such possibilities reveals how radically cosmology has evolved. Questions once considered philosophical or mythical are now explored through statistical analysis, satellite measurements, and mathematical models. There is something profoundly cinematic about this transformation. A species born from evolutionary survival instincts now builds machines capable of measuring fluctuations from near the dawn of time itself. And yet, despite all this technology, a deeper frustration remains hidden beneath modern cosmology. The laws of physics themselves may prevent humanity from ever fully seeing the beginning. Because the closer observations approach the Planck epoch, the earliest known fraction of a second after the Big Bang, current theories stop functioning properly. Gravity becomes quantum. Space-time may fluctuate violently. Ordinary concepts of distance and duration lose stability. The universe itself becomes opaque to understanding. This is what makes the search feel almost tragic in a beautiful way. Humanity may be intelligent enough to realize the mystery exists, yet limited in ways that prevent complete access to the answer. Some physicists openly wonder whether certain aspects of cosmic origins may remain permanently beyond observation, not temporarily hidden, but fundamentally inaccessible because of how reality itself operates. Imagine standing inside a sealed room with only echoes to study the world outside. You can reconstruct shapes indirectly, infer movements, detect vibrations, but some structures remain permanently beyond direct view. Cosmology increasingly feels like that. Scientists observe ancient radiation, galactic distributions, gravitational effects, and quantum signatures. From these fragments, they attempt to reconstruct a story stretching back toward the origin of existence itself. But perhaps the first moment can never be fully observed from within the universe. And still, humanity refuses to stop looking. Some researchers explore quantum gravity theories, hoping to mathematically penetrate the earliest epoch. Others investigate black holes because singularities inside them may share hidden connections with the Big Bang. Some search for subtle anomalies in cosmic expansion that might hint toward physics beyond current models. Every new telescope, every detector buried underground, every gravitational wave observatory becomes part of the same ancient human instinct, the need to see farther, not only across space, but beyond the visible edge of reality itself. There is also a strange irony hidden inside this search. Human beings are made from atoms forged in stars. Those stars formed from matter created in the early universe. The universe evolved conscious organisms capable of turning back toward their own cosmic origin and asking how the process began. In a sense, the cosmos became self-aware enough to investigate its own birth. And perhaps that is why the mystery feels so emotionally powerful. This is no longer just astronomy. It is existence attempting to understand itself. Somewhere beyond the oldest observable light, beyond quantum uncertainty, beyond the limits of current mathematics, something happened that gave rise to everything humans have ever known. Every ocean, every civilization, every memory, every living creature emerged from processes hidden near that unreachable horizon. Maybe future physics will eventually reveal what existed before the Big Bang. Maybe primordial gravitational waves will expose traces of earlier cosmic states. Maybe entirely new theories will overturn current assumptions completely. Or maybe the beginning of the universe lies behind a boundary no intelligence can ever fully cross. Right now, nobody knows. But night after night, deep beneath deserts, high on mountaintops, and far above Earth's atmosphere, humanity continues building instruments to push a little farther into the darkness, trying to catch one more ancient signal, one more faint ripple, one more clue from the edge of time itself. For most people, the Big Bang feels like the ultimate beginning, the first moment, the cosmic starting line, the instant when darkness broke open and reality began unfolding into stars, galaxies, planets, and eventually conscious life. Even people who know little about cosmology often imagine the Big Bang as a kind of absolute creation event, the moment existence itself switched on. But the deeper modern physics investigates the universe, the less certain that story becomes. Because, hidden beneath the success of Big Bang cosmology, is a quiet possibility many scientists still wrestle with. What if the Big Bang was not the beginning at all? What if it was only the point where our visible chapter of reality started becoming observable? That idea changes everything emotionally. The universe no longer feels like a story with a clean opening scene. Instead, reality begins resembling something far older, stranger, and potentially endless. A structure where beginnings may only be local transitions inside a much larger process humanity cannot fully see. And oddly enough, modern science did not arrive at this possibility through philosophy or mythology. It arrived there through equations. The standard Big Bang model explains many things extraordinarily well. It predicts cosmic expansion. It explains the abundance of light elements like hydrogen and helium. It accurately describes the cosmic microwave background radiation, ancient light still drifting through space from the early universe. But there has always been one uncomfortable problem hiding underneath the model: the singularity. If the universe truly began from infinite density and temperature, physics itself breaks down. The equations stop working. Space and time collapse mathematically into impossible conditions. And whenever infinities appear in physical theories, scientists become suspicious. Infinity inside an equation often signals that the theory has reached its limits, rather than revealing ultimate truth. So over time, physicists began asking a dangerous question. What if the singularity never actually existed? What if the Big Bang was not a creation point, but a transition point, where current physics simply loses visibility into earlier states? That possibility opened the door to an entirely different vision of cosmic history. One idea proposes that the universe existed before the Big Bang, in another form entirely. In cyclic cosmologies, previous universes may collapse inward before rebounding into new expansion phases. Instead of one beginning, reality becomes an endless chain of cosmic eras: expansion, collapse, rebirth, again and again, across unimaginable timescales. In some versions of loop quantum gravity, quantum effects prevent total gravitational collapse into a singularity. Space-time itself resists infinite compression. The universe contracts until it reaches an extremely dense quantum state, then bounces outward into a new phase of expansion, a big bounce rather than a big bang. And if that happened, our universe may contain echoes from earlier cosmic cycles hidden somewhere inside its deepest structure. There is something haunting about this possibility, because it transforms the cosmos into something almost organic. Universes dying and regenerating like enormous breathing systems across eternity. But cyclic cosmology is only one path. Other theories suggest the Big Bang emerged from higher dimensional physics beyond the visible universe entirely. In certain string theory models, our universe may exist as a membrane, a brain, floating through a larger multidimensional reality sometimes called the bulk. According to some versions of this idea, the Big Bang occurred when massive higher dimensional brains collided. The collision released enormous energy, creating the hot, dense conditions that evolved into our observable universe. If true, the Big Bang was not the beginning of all existence. It was more like an event inside a larger cosmic environment already operating beyond human perception. And suddenly, the scale of reality expands again. The visible universe stops feeling self-contained. It becomes one layer embedded inside deeper structures hidden outside ordinary space and time. What makes these theories fascinating is not merely their strangeness, it is that they emerge from serious attempts to unify gravity and quantum mechanics, two frameworks that currently refuse to fit together cleanly. Whenever physicists push equations toward the earliest moments of the universe, reality becomes unstable and unfamiliar. Space bends, time loses meaning. Quantum effects dominate gravity. The closer science approaches the beginning, the more the universe stops behaving like a machine and starts behaving like something profoundly alien. And this has forced cosmology into an uncomfortable realization. Human intuition may simply be wrong about beginnings. People instinctively expect existence to function like stories. Every story starts somewhere. Every event has a cause. Every structure has an origin. But reality itself may not obey narrative logic at all. Some physicists now suspect the universe could be eternal in ways human minds struggle to visualize. Not eternal in the old classical sense of a static, infinite cosmos, but eternal through constant transformation. Inflationary cosmology already hints at something similar. In eternal inflation models, space continually generates new universes indefinitely. Our Big Bang would represent only one local bubble emerging inside a much larger inflating background. There may never have been one single universal beginning. Instead, beginnings could happen continuously. Some regions inflate, some stop inflating. Some become universes capable of forming stars and galaxies. Others remain empty or unstable. Reality becomes an endless process rather than a singular event. And emotionally, this idea can feel strangely disorienting. Human beings naturally crave origins because origins create meaning. We want the universe to have a first page. But modern cosmology increasingly hints that existence may not contain one absolute starting point at all. And then there are the even stranger possibilities. Some researchers exploring quantum gravity have proposed that space and time themselves may emerge from deeper structures beneath ordinary reality. If this is true, then asking what happened before the Big Bang could become fundamentally meaningless because time itself only emerged afterward. Not hidden, not destroyed, simply non-existent in the ordinary sense. In these models, the Big Bang resembles less a beginning and more a phase transition, like water freezing into ice. Before the transition, reality existed in another state, where classical space and time did not yet operate as they do now. The implications become difficult even to describe in language because human thought depends so heavily on temporal structure. Every sentence assumes sequence: before, after, cause, effect. But near the origin of the universe, those concepts may collapse entirely. Some physicists openly admit that the brain evolved under conditions completely disconnected from these scales of reality. Human intuition developed to understand movement, survival, and social behavior, not quantum gravity or the birth of cosmic structure. And perhaps that is why the universe keeps feeling more surreal the deeper science explores it. Because reality at its foundations may not resemble anything evolution prepared us to naturally comprehend. There is also another possibility, one many scientists discuss carefully because it edges close to philosophy. The observable universe may not represent total reality at all. What humans call the universe may only be the portion accessible from our cosmic location. Beyond the observable horizon, conditions could differ radically. Beyond inflationary boundaries, entirely different universes may exist. Beyond quantum spacetime, deeper structures may operate permanently outside observation. In this picture, the Big Bang becomes not the origin of everything, but merely the beginning of everything we can currently detect. And that distinction matters, because it means cosmology may never truly end. Every answer reveals another layer underneath it. Every beginning points toward a deeper framework behind it. The universe increasingly resembles nested realities rather than a single, isolated structure. What makes all this so emotionally powerful is that science has arrived here reluctantly. Physicists are not inventing these ideas simply because they sound mysterious or philosophical. They emerge because current models leave unresolved gaps. The singularity problem remains unsolved. Quantum gravity remains incomplete. Dark energy remains mysterious. Time itself behaves strangely under extreme conditions. The deeper researchers investigate, the more the cosmos refuses to settle into a simple story. And perhaps that is the greatest transformation modern cosmology has created. The universe no longer feels static or fully knowable. It feels layered, dynamic, potentially infinite in ways beyond ordinary imagination. Maybe the Big Bang truly was the first moment of all existence. Maybe another universe came before ours. Maybe universes are born endlessly through inflation. Maybe time itself emerged from a deeper, timeless reality. Right now, science cannot say with certainty. But one thing has become increasingly clear. The closer humanity approaches the beginning of the universe, the more the concept of a beginning itself starts dissolving. And somewhere beyond the oldest observable light, beyond singularities, beyond quantum foam and collapsing equations, there may exist a level of reality where universes are not rare events at all, but temporary patterns appearing and disappearing endlessly inside a cosmos far older than human beings ever imagined. A cosmos where the Big Bang was not the first chapter. Only the first chapter we were capable of seeing. At the edge of every scientific explanation, there is a silence. Not the silence of ignorance in the ordinary sense, but the silence that appears when human understanding reaches the boundary of what it can currently describe. Modern cosmology has carried humanity farther into the universe than any civilization in history ever imagined possible. We know stars are born inside collapsing clouds of gas. We know galaxies drift through expanding space. We know black holes bend time itself. We can measure radiation left behind from the early universe and calculate the age of the cosmos with astonishing precision. And yet, after all of it, one final mystery still remains standing in the darkness. Why does any of this exist at all? Not merely planets or galaxies, existence itself. The deeper science explores the universe, the stranger that question becomes. Because every answer about cosmic origins eventually leads to another deeper layer underneath it. If the Big Bang created the observable universe, what triggered the Big Bang? If quantum fluctuations produced it, where did the quantum laws come from? If universes cycle eternally, why does the larger system exist? If time itself emerged from a deeper state, what gave rise to that deeper reality? The mystery never fully disappears. It only changes shape. And perhaps that is what makes the universe so haunting. Humanity keeps pushing farther into the structure of reality, yet the horizon always moves away again. For most of human history, people imagined the cosmos as something understandable through direct observation. The stars moved overhead, seasons returned, the heavens appeared ordered and eternal. But modern science slowly revealed that beneath ordinary appearances lies a universe almost violently strange. Invisible dark matter surrounds galaxies. Dark energy accelerates cosmic expansion. Quantum fields fluctuate inside empty space. Black holes distort time and erase visibility itself. And somewhere near the beginning of existence, the laws of physics collapse into uncertainty. The universe no longer resembles a clockwork machine. It resembles something deeper, stranger, and far less intuitive than human beings once believed possible. One of the most unsettling realizations in modern cosmology is that reality may not care whether humans can fully understand it. Evolution shaped the brain for survival on Earth, tracking movement, recognizing patterns, navigating social groups, avoiding danger. Nothing in human evolution prepared consciousness to intuitively grasp quantum mechanics, curved spacetime, or the possibility of infinite universes. And yet, somehow, the human mind still reached far enough to discover them. That alone feels almost miraculous. A species made from star matter evolved the ability to look outward and realize the stars themselves are temporary structures drifting through expanding cosmic darkness. The atoms inside human bodies were forged inside ancient stellar explosions billions of years ago. In a very literal sense, the universe eventually produced organisms capable of questioning the universe itself. Reality became self-aware enough to wonder where it came from. And maybe that is part of why cosmology feels so emotionally powerful. These are not distant abstract equations disconnected from ordinary life. Every human memory, every civilization, every ocean, every living creature exists because the universe unfolded exactly the way it did after the Big Bang. If gravity had behaved slightly differently, stars may never have formed. If certain quantum constants changed slightly, chemistry could collapse. If expansion had moved too rapidly, matter may never have gathered into galaxies at all. Human existence depends on a chain of cosmic conditions so delicate that many physicists still debate why the universe appears compatible with complexity in the first place. Some interpret this as evidence of deeper physical selection through multiverse theories. Others suspect undiscovered laws may eventually explain the apparent fine-tuning naturally. Some believe humanity still lacks critical pieces of understanding entirely. Right now, nobody truly knows. And that uncertainty sits at the heart of the final mystery. Because despite all the confidence science projects outwardly, cosmology remains filled with unanswered questions. Scientists still do not know what dark matter is made of. They still do not understand dark energy. They still cannot fully reconcile gravity with quantum mechanics. They still debate whether time itself is fundamental or emergent. The map of reality remains unfinished. There is also something deeply unsettling about the possibility that certain truths may remain permanently inaccessible. The observable universe already limits how far humans can see because light travels at finite speed. Beyond the cosmic horizon, entire regions of reality may exist forever outside observation. And, if inflationary multiverse theories are correct, then most of existence could remain causally disconnected from us forever. The cosmos may contain levels of reality no experiment can ever directly reach. Some physicists resist this possibility because science traditionally depends on observation and testability. Others argue the universe is under no obligation to remain fully observable to creatures living inside it. And, perhaps, that tension reveals something important. Humanity often assumes understanding should eventually become complete, but reality itself may not operate in a way that guarantees total comprehension. The universe may simply be larger than any mind evolved within it can fully contain. Still, humans continue searching. That persistence says something extraordinary about consciousness itself. Ancient humans once feared eclipses and wandering comets. Now humanity builds detectors capable of sensing collisions between black holes billions of light years away. We launch telescopes into deep space, searching for light from the earliest galaxies. We measure tiny fluctuations in ancient cosmic radiation to reconstruct conditions near the birth of the universe. Again and again, science pushes farther into darkness, and every time, the universe reveals something nobody expected. That pattern alone should probably make us cautious about certainty, because history shows that reality repeatedly overturns human assumptions. Earth was not the center of existence. The Milky Way was not the entire cosmos. Space was not static. Time was not absolute. Empty space was not truly empty. Each discovery widened the scale of reality while shrinking humanity's sense of central importance. And perhaps the final mystery will do the same. Maybe future physics will eventually reveal that universes emerge naturally from deeper quantum structures. Maybe the cosmos cycles endlessly through expansion and collapse. Maybe space and time themselves are emergent illusions generated from information relationships beneath reality. Maybe consciousness plays a role humans still do not understand. Or maybe some questions simply extend beyond the limits of what intelligence born inside this universe can ever fully answer. There is something strangely beautiful about that possibility, not because ignorance is satisfying, but because mystery itself may be woven into existence at the deepest level. The universe is not merely a collection of objects floating through empty space. It is an unfolding structure still revealing itself, even to the minds attempting to study it. And despite all the equations, all the telescopes, all the particle accelerators and mathematical models, the final mystery remains emotionally simple in a way almost anyone can feel. Why is there something instead of nothing? Why should reality exist at all? No scientific theory has completely answered that question yet, Some physicists suspect the answer may ultimately emerge from deeper laws. Others wonder whether existence simply is, requiring no external explanation beyond itself. But even if science eventually uncovers new layers of understanding, the emotional experience of confronting the cosmos may never fully disappear. Because late at night, beneath a sky filled with ancient starlight, the universe still feels enormous in a way mathematics alone cannot entirely capture. Those stars are not decorations. They are nuclear furnaces suspended in expanding space. Some already died before humans existed. Some host planets orbiting in darkness right now. Some may illuminate civilizations staring upward, asking the same questions humanity asks. And beyond all of them lies a reality even larger than the visible cosmos. Hidden behind cosmic horizons, quantum uncertainty, and the limits of human understanding. Maybe the universe had a beginning. Maybe it did not. Maybe reality extends infinitely beyond everything humanity can observe. Or maybe existence itself is stranger than any current theory has yet imagined. Right now, nobody knows for certain. But perhaps the most remarkable part of the entire story is this. Out of all the chaos and violence of cosmic history, the universe eventually created conscious beings capable of feeling wonder. Creatures able to stand on a small planet orbiting an ordinary star and ask questions about the origin of everything. And somewhere in that strange relationship between human curiosity and cosmic mystery, the universe revealed one final truth about itself. It is not only vast, it is still unfinished. Thanks for exploring the mystery of the universe with me tonight. The deeper we look into space, the more reality begins to feel stranger than fiction itself. If you enjoyed this journey through the origins of existence, don't forget to subscribe for more relaxing cosmic mysteries and sleep documentaries. Until next time, keep looking up at the stars.